Hello, my name is Bill Kinney and this is part 31 of my series of videos about parametric curves. I decided I wanted to do one more video about modeling the trajectory of a ball, so this is part 10 of that subseries. If you're in pre-calculus, if you've not even gotten that far into calculus, you might want to consider skipping this video, or if you do not skip it, just try to get the basic idea of things. I'm going to go quickly through some more deep ideas in physics and in calculus in this video as a way of helping myself in later videos to do more complicated kinds of modeling. So we're going to talk about Newton's laws, in particular Newton's second law, and how it's related to something called a differential equation for projectile motion with no air resistance. And we're going to give an indication of how to find the distance traveled function, dist of t in this situation, that it's possible to do by hand, though it's very difficult. So here's the situation again. Pause the video, look this over. The first goal here is to try to understand where these equations come from. What are the physical principles that allow us to derive these parametric equations? So down here I've pre-typed some things because it's such a long thing in this video to type. Focus on this part right here. Now use your imagination, maybe make a drawing. Suppose we have an object, a ball, of mass m in the air under the influence of gravity. Okay? Now we're going to assume there are no other forces. Ha ha ha. Of course there are other forces. There would be air resistance. But we're going to ignore air resistance and hope that we can get a pretty good model. Alright, the force due to gravity can be measured, and it can be measured as equaling, as in vector form, this particular vector right here. Now I'm using the vector notation from John Rogoski's multivariable calculus book. Many other people use other kinds of notation for vectors. You might see a j hat or a k hat in here, negative mg times that. What does this mean? First of all, you've got a 0 in the first component. That means that the vector, the arrow, has no horizontal displacement. It's either pointing straight up or straight down. The mass m and g, the acceleration due to gravity, are positive quantities, so by putting a negative sign in there, this indicates that the second component is negative, so this vector, this arrow, points straight down. G is about 9.8 meters per second squared in standard units. There's something called Newton's second law, hopefully you've heard about that, that says F equals ma, the force on the object is equal to its mass times its acceleration. Therefore we can set this thing, this vector, equal to this vector. We can factor the m out of this vector. There's really an m times 0 that you don't see there in the first component, and we can cancel the m down here to get ultimately this particular equation, that the acceleration vector is 0, negative g. 0 for the first component, negative g for the second component. It is also a constant vector. It points straight down all the time. This equation is really what we call a differential equation. It involves a, which is the derivative, the rate of change of the velocity, thus the name differential equation. The goal here is to try to solve this equation. This says the derivative of the velocity vector is this constant vector. We can think of this component by component. The first component of the derivative of the velocity vector is 0. Therefore, if you integrate 0, you get a constant. That will be the first component of the velocity vector. That's indicated by the fact that we have a 0 here and a v sub 0 here. In fact, whatever the first component of the velocity vector is, that will be the first component of this vector. We also see that its second component is negative g. We can integrate that and get that the second component is negative g times t plus a constant. The second component of that constant must be the second component of the initial velocity, is what this says down here. And so we get this equation for the velocity vector. I know I'm going pretty fast here. I am assuming you understand the basic idea of integration. Alright, this is also a differential equation. It involves a derivative too. The velocity vector is the derivative of the position vector. V is dr dt. So I can write the equation this way, and then I can integrate again. When you integrate negative gt, you get negative g over 2 times t squared, which is what you see here. And when you integrate v sub 0, the initial velocity, you get the initial velocity times t. T would get multiplied by each component of that initial velocity. We again have a constant of integration. If we assume that the initial position is a position vector, call it r sub 0, that turns out to equal the constant of integration, and we can rewrite our final equation for the position vector in this form. What I want to quickly do now is compare this with what we have up here in the problem statement, these parametric equations. I can type compare this with these parametric equations. Compare this particular thing with these parametric equations. First of all, let's focus on the y. Y as g of t is 19.6t minus 4.9t squared. That minus 4.9t squared, that's negative g over 2 times t squared right there. That's where that comes from. Where does the 19.6t come from? It comes from the initial velocity vector times t. So evidently the initial velocity vector has a second component here of 19.6 meters per second. The r0 for the second component is 0, and for the first component as well. There's no constant term in either case. r0 is the 0 vector in this case. We start the motion at the origin, in fact. What about the first component? You don't see a t squared term because of the 0 here. You do see a t term, 30 times t. Evidently 30 is the first component of the initial velocity. So the initial velocity vector has a first component of 30 and a second component of 19.6. We can use Mathematica to do these calculations as well. A of t, I've already entered, is 0, negative 9.8. I can integrate that with an indefinite integral symbol in Mathematica and get a velocity vector equal to this plus a constant. Now Mathematica doesn't put the constant in, but we know there's a constant there. We know, in fact, what it is. That constant has a first component of 30 and a second component of 19.6. I can then integrate the velocity vector as well. And lo and behold, we do get the parametric equations up here. X is 30t, matches this 30t here. Y is 19.6t minus 4.9t squared, matches this expression right here. Plus a constant. The constant of integration, though, is going to be 0 because the initial position is the origin. So that's my quick summary of the physics. We'll take that physics principle about Newton's second law and apply it to more complicated situations later on. I also want to spend a few minutes discussing with you how to integrate the speed function in this situation by hand to find the distance traveled function. Now this is a very complicated thing to do in this situation. The distance traveled is going to be the integral of the speed plus an appropriate constant of integration. Okay, so the goal would be then to integrate the speed function, to integrate this thing. How in the world would you do that? It is difficult. Okay, and I don't want to show you all the details. I'm showing you a summary of the details, and then hopefully you would be inspired to take it from there. To do this integral, to integrate this function right here, the square root, it's a good idea to first do a substitution. If you let u equal 19.6 minus 9.8 t, that's a good substitution to make initially. If you do that, then du will be negative 9.8 dt, and therefore dt will be 1 divided by negative 9.8 times du, and we can rewrite the integral in this form. Hopefully you've seen this kind of integrand before and realize that in that situation, especially because 900 is 30 squared, a nice perfect square there, that using a trigonometric substitution is good to do next. Letting u equal 30 times tangent of theta, a new variable theta, is a good substitution to make here. Du would be 30 secant squared theta d theta, and after that substitution you would get this. Now it's a matter of using a trigonometric identity. We can factor the 900 out of the expression under the square root and take the square root of 900 to get 30. 30 times this other 30 is 900. And 1 plus tangent squared theta is secant squared theta. That's a trigonometric identity. So we're left with this integrand now, which still looks pretty complicated. If we assume, for the purposes of getting an answer, that the secant theta is greater than or equal to 0, then the square root of secant squared theta, which is really the absolute value of secant theta, could be thought of as just a secant theta in that case. And the integral becomes this. And we integrate secant cubed. To do that integral, it is possible to do by hand. You do an integration by parts with these expressions, and you'd rearrange to solve for secant cubed theta in terms of the integral of secant theta. We're getting it more and more simple. This last integral, the integral of secant theta, there's an amazing trick to solve this integral. If you multiply the integrand by this expression, secant theta plus tangent theta over secant theta plus tangent theta, which is really just a disguised form of 1, So you don't change the integrand. A simple substitution, u equals secant theta plus tangent theta, allows you to integrate that amazingly enough. And you get an answer involving a logarithm. At the very end, you'd want to get everything back in terms of t. Is that really what happens? Yes, it is, and you can do it. It takes quite a while to do. What does Mathematica give as the answer? We've done this before. This complicated thing involving a hyperbolic arc sine, and I said before that a hyperbolic arc sine is related to logarithms, and therefore you really are still getting the same thing, even though it looks different here initially. That was fast, but I needed to go fast if I'm going to get it in 10 minutes. I hope that you got something out of it. We'll continue with circular motion in the next video.